Hello, everybody. So what we're going to be looking at today is the exam one practice solutions. I'm going to go over these solutions, but I already tried making this video one time and the video broke halfway through where the sound cut out and I couldn't fix it, so I have to redo it. However, I don't want to rewrite everything that I'd written so far, so I'm just going to kind of hit the high points of that first bit that I already wrote. Okay, so here's the deal. And I know that this is going up very late, but maybe it's still helpful for somebody. And yeah, maybe it's helpful for somebody. So anyway, let's just go ahead and get going here. So our first problem, 1a, says to find the equation of a plane containing 3 points, and then they give us the 3 points. So what's that look like for a solution? So we've got these 3 points, and we want to figure out the equation of the plane. So if you look at a picture of a plane like this, we can put the 3 points, the A, the B, and the C, those were given to us on the plane. All right, that's where they all are. Those 3 points are on the plane. And then we need to find the equation. Well, how do we do it? Well, you go from having 3 points on the plane to having 2 vectors in the plane. So you just make vectors like AB, for example, that's one of our choices, and AC, that's another one of our choices. At that point, you're going to have 2 vectors in the plane. Then from those 2 vectors, we want to get a normal to the plane, which means it's at a right angle to the plane. And the way you do that is simply the cross product of those 2 vectors that you found. So what do? We go from the A, the B, the C to having the AB and the AC, and then we do the cross product. I don't know why I put magnitude around that. We just want the cross product. We want a vector perpendicular to these 2 vectors. Okay. And then from there, we can come up with the equation of the plane. So very straightforward process here. So what we do is, first of all, find the vectors AB and AC. You get that by subtraction, right? So the vector to AB, you just do 1 minus 2 for the first component, -1 minus 0 for the second component, 6 minus 3 for the third component, and you get your vector -1, -1, 9. You do the same thing to get AC, and this is the result here. Now, you don't have to get AB and AC. You could have done like BA and BC. You could have done, CA and CB, whatever you want. You just need 2 vectors in the plane. So these are the 2 vectors that I came up with here, this one and this one. Okay, now once you have those 2 vectors, you need the normal vector, and you get the normal vector with a cross product. So I'm not going to go over this in great detail. You should be able to calculate a cross product. If not, see the earlier videos, or look in your textbook, or find an alternate video on YouTube, or cheat and use Wolfram Alpha. Whatever you have to do to get the cross product here. So I did the cross product of the 2 vectors that we just found. That's AB and that's AC. You could have done AC cross AB, that would have been fine, or whatever vectors you have. So this is the work for calculating the cross product. I'm not going to go over it. And then this is what you get for your result, -48, 30, -2. All right. Now, once you have the normal vector to your plane, you want to write the equation of the plane. So there's a couple ways to do this. The easiest way, I did it the easiest way in my opinion, is to simply write out like the final form of the equation, ax plus by plus cz equals d. Okay, that's how the plane is going to look at the end. The a, the b, and the c are the coefficients from your normal vector. So they are the -48, 30, and -2. That's your A, your B, and your C. So you fill those in. So take those numbers, put them in here, and you get this equation, negative 48x plus 30y minus 2z equals D. That's not the final result for the plane, because D is a number that we still have to find. It's just like if you were finding the equation of a line, right? If you wrote y equals mx plus b to start with, that's fine. And then if you found the m, and like let's say the m was 3, and you have this, that's also fine. But you're not done with the problem until you find what the b is, right? You still have to find that number using like a point that's on the line or something like that. So that's exactly the same process we're going to use. So we need to find this D. How are we going to do it? Well, you plug in a point, any point. So I could have plugged in any point for x, y, z that was in the plane. So I just looked up at my list of points. This is one of them, A. So A is on the plane by definition, because that's what we're trying to solve here. So plug that in for x, y, and z. We get this. Negative 48 times 2, 30 times 0, negative 2 times negative 3 equals D. We don't know D. But you work this all out, and you end up with negative 90. Negative 90 equals D. So we found it. So you go back up to your equation where you had it with the D unknown, and just replace the D with negative 90, and there you go. That is your equation of the plane. So very straightforward there, I think. Yeah. So that's it for 1A. Now, also, if you look at the solutions or answers, you'll notice I wrote 24x minus 15y plus z equals 45. For the equation of the plane. That's just because when you get to this point where we are now, you realize that all of these, the 48, the 30, the 2, and the negative 90, these are all divisible by 2, so you can just divide the entire equation by 2, and the numbers will be a little smaller. I do that, but not yet. So 1b says, does the point D323 lie on the plane? Okay, does the point 323 lie in the plane? So all you do is you take 323, the point, put it in the equation of the line, plane, put it into the equation of the plane, and just see if it satisfies this equation. So I take 323, I put it into the equation, I get this line. I don't know at this point if the left side is going to equal the right side, so I put a little question mark over the top. Then I worked out the left side, and it came up to negative 90, which is equal to negative 90. So that equation is satisfied by 323. And that tells me that 323 is on the plane. Okay, so that's 1b. So 1c. So 1c says we're trying to find, it's hard to see here, we're trying to find the distance from the plane, which I've now divided everything by 2 if you look at what I've got written there, to the origin. The origin, I wanted to give it a name. I could have called it O for origin, but I didn't. I called it F. Why F? Because we already used A, B, C, and F. A, B, C, D, and F. We didn't use E. So I did that. So called it F. Okay, so we want the distance from this plane to this point. Now there's a formula for it, but here's where the formula comes from. I'll just explain this real quick. Okay, so there's a point in the plane. You could pick any single point in the plane you want. I picked D. D was, remember, 323 from the previous problem. Why 323? I don't know, just because it was the one that I could see. So there's a point there, all right? And then you have your plane and your normal vector. I don't know which direction the normal vector points. I just drew it the way I drew it, okay? Now, you've got D, which is on the plane. Oops. D, which is on the plane. F, that's actually 0, 0, 0 for us, but not on the plane. And we have the normal vector. These are the things that we've got in our picture so far. So the procedure for finding the distance from this point to this plane is as follows. You make a vector from D to F or from F to D. I think I do F to D. So I think I find that one. It doesn't really matter. DF, FD, whichever one. So I guess I wrote DF over here. So I'll use DF, even though I think I switch and use FD later on. So you find that vector, okay? Now, once you find that vector, you do a projection of this vector onto this vector. And what that looks like is this. Let me just get a color. You will find this vector, technically. This vector. So the n was that small one. This is this, actually, the projection of df onto n. So it'll point in the same direction as n, which means orthogonal to the plane, but the length will be different. And the length will be, well, the length will be from here to here, which is exactly the distance from this point to this plane, right? So you do that projection and then you want its magnitude. So you can write that a few different ways. You can say it is the projection of that vector onto n, and then you have to take the magnitude of it. Or you can write it as CMP df onto n. So that's the component of df in the direction of n. That's the what we call scalar projection of df onto n. It could be positive or negative, so you do absolute values. And then if you write out what that is, this is what it is as a formula. And that formula is the distance that you want, okay? So you just need to calculate that vector df. N you already know for the plane, and then you just work this out and you get whatever you get. So we did that here. I did FD instead of DF because if you do F to D instead of D to F, then you go 3 minus 0, 2 minus 0, 3 minus 0, which means you get it up with all positive numbers instead of all negative numbers. So I was just kind of being lazy because I knew it didn't matter. So you calculate that vector. You know, it turns out to be 3, 2, 3. That's only luck because our point was 0, 0, 0, right? If the point we were doing was like 1, 1, 1 or 1, 2, 3 or whatever, then, you know, this is not just going to be the same as one of these. But in this case it is. FD is 3, 2, 3. So we got that vector. We know n from our plane. That was, you know, the ABC from the plane. The little a, little b, little c coefficients on the plane. And then, yeah, so we work out this formula. So we have 3, 2, 3, that's df, dot with the coefficients from the plane over the magnitude, right? So that's n, and that's the magnitude of n. So I worked this out. I think I got 1.59. I didn't check that answer. But I got... yeah, I guess that must be right. So I got 45 over square root 802, which works out to 1.59. There, the reason it's 90 over 3208 was because I must have worked that out without using the coefficients before I divided by 2 instead of after I divided by 2. But it doesn't matter. So same answer, and that's it. That's problem 1. Now, if we have long calculations, you know, I might just start doing some stuff on the computer. But let's just keep going here. That was kind of a long problem. Let's switch colors. 2. All right, so we've got a vector G, it says, 2, 2, 2. We have a vector H, it says, 5 minus 1, 3. And we want scalar and vector projections. So these are just making sure you can do the formulas that you can look up. So scalar projection is this component of H onto G dot H over magnitude G. This is exactly like up here for that distance formula where when we did this, right, df onto n, it was df dot n over magnitude n. So exactly the same thing here, just with these numbers. So 222 dot 5 negative 1 3 over magnitude of G, which is 2 squared plus 2 squared plus 2 squared. And you work that out. Looks like the denominator will be 4 plus 4 plus 4, which is 12. And the numerator will be 10 minus 2, which is 8, plus 6, which is 14. And there you go. Okay. Now when you do the vector projection of H onto G, that's the PROJ H onto G, then the magnitude comes from the same calculation as what we just did, but then you multiply it by a unit vector in the direction of G is what you have to do. And so when you simplify this formula here, what you get is that basically that is a square root of G, not square root of G, it's the square root of like the components of G squared. But when you multiply these two things together, that actually works out to G dot G. So you end up with G dot H on top, G dot G on the bottom, and then times G. And so all this is a number on the left, and all that's a number on the left. So if you work that out, I guess I don't really want to, but this one came up 7/3, 7/3, 7/3, it says. But, you know, this is just a dot product over a dot product times G. So it's not too complicated. So hopefully that was enough detail there for that. Number 3, determine if the lines are parallel, intersecting, or skew. So the way I think of it is like this. So we have two lines, right? L1 and L2. I'm gonna kind of like a flow chart. So like the first thing you do is, you know, you check if I don't know what notation is for flowchart, so don't pay attention to boxes and circles and whatever. But what you do is basically this: you're going to look at their direction vectors. So if you look to see same direction vectors, you know, if yes, then you do one thing. If no, then you do something else. So what do? Well, if they have the same direction vector, then they could be parallel or they could be the same line. So then you go same line. If yes, then same line. There's nothing to it. If no, then they are parallel. Okay. Now back to the direction vectors. If they're not the same direction vectors, then they either intersect or not. So intersect. If they do intersect, then they are intersecting lines. If they don't intersect, then they are skew. All right, so that's like the logic for how you do this. So with that in mind, what we do is we are just going to look at our lines here. So in line A, so for part A actually, so L1, I don't want to write it, but L1 has a direction vector. I guess I'll call it like D1. So the direction vector for line 1 comes from the coefficients on the t's in its direction vector. So 4, -2 and 6. And for L2, the direction vector, I'll call it D2, just for direction, is 12, right? 12s. So 12, it's a S instead of a T. So 12, -6, and 15. And these are not a scalar multiples of each other. They're not, right? Because if you look, if you multiply 4 by 3, you get 12. 4 times 3 is 12. And if you multiply -2 by 3, you get -6. But if you multiply 6 by 3, you actually get 18, right? Not 15. So the direction vectors are not scalar multiples of each other. So that's the first thing. So directions are not the same. Because the direction vectors are not scalar multiples of each other. So that tells me that they either have to be skew or intersecting. They can't be parallel. Okay. Skew or intersecting. So if they're intersecting, then what you need to do is find the point of intersection. So to find point of intersection, then you're solving a set of simultaneous equations. What they are the x components here have to be equal. So you have 3 equations. One is 6 plus 4t. That's the x component from L1 has to equal 3 plus 12s. That's the x component from L2. Then for the y components, those have to be equal, right? I'm talking about at a point of intersection. This has to be true. So if they intersect, the y values have to be equal. And then also the z values have to be equal, okay, if those are intersecting lines. So these are simultaneous equations. You have to try to solve these. Now, how are you going to solve these? Well, I mean, that is up to you. You can do it by, well, yeah, it's just kind of up to you. I'll just use Wolfram alpha here. I mean, it's it's 2 variables, 2 unknowns. If you look at just the first 2 equations together, which is what I want to try to do. Wolfram. I mean, I could just solve them all, but I wanted to show you an idea. So I'm going to solve the first 2. So if I say solve, and then I just list the equations, 6 plus 4t equals 3 plus 12s. And then my other equation is 8 minus 2t equals 9 minus 6s. Now that's only 2 of the equations, right? Only 2 of them. If you solve 2 of them, you almost certainly will find a solution, okay? Or not. Okay. Well, there you go. And I'll just type in the last one then, might as well. Usually you find a solution to them. But if there's no solution to the first 2, then there's no solution to the last 2, right? So it says no solutions exist. If I take off like one of these first 2 where the problem were, like generally if you pick 2 of them, then like you might find a solution. But like this S and this T solve the 2 equations that I listed here, like the last 2 equations on the list. And if you took those S and T values and you tried to plug them into the top equation, it just would not be true. Okay, so normally that's what I do is I just pick 2 equations, try to solve them for S and T. If I get an S and T value, I plug it into the 3rd equation. So yeah, so I just typed these into Wolfram alpha because I was too lazy to solve them. I got no solution. So what's that mean? Well, they have different directions and they have no points in common. And that tells me that these lines are skew lines. Okay. All right. What's next? Right, so let's just do this. This is what? 3b. So 3b, the process is the same, but since I gave them to you in symmetric form, then it's generally not going to be as easy to tell. So if I write them out, just x minus 4, I'm writing out L1 right now, over -1, y plus 5 over -4, z minus 1 over 6. If I wanted to turn that into parametric equations like we had for the previous problem, what you would do is you would say, so all this is for L1, you would say, since they're all equal to each other, you kind of just mentally, not mentally, I mean, you can do it formally, just add equals t there. That's where the parameter goes. So like your first equation is x minus 4 over -1 equals t, which rearranging it is x minus 4 equals -t, which rearranging that is x equals -t plus 4, right? So that's one of your equations. Your y equation is y plus 5 over -4 equals t, which is y plus 5 equals -4t, which is y equals, I don't know why I put two negatives there. Oh, -4. No. Which is -4t minus 5, and that's your y equation. And then for your z equation, or sorry, not z equation yet, your z is z minus 1 over 6 equals t, which is z minus 1 equals 6t, which is z equals 6t plus 1. I wrote 1, I wrote 5. So there you go. So if you want a direction vector, so L1, the direction vector, I'll call it L1 again, D1, the direction vector is -1, -4, +6. Okay. Now for L2, if you do all the same stuff, which I will, but I'm not going to write it, what we would get is the D2. Oh, by the way, there is a shortcut here, right? The -1, -4, 6, if you look, they are these numbers, -1, -4, 6. But the only reason they're those three numbers, as opposed to like being modified in some way, is because the coefficient of the x in the numerator is a 1, the coefficient of the y in the numerator is a 1, and the coefficient of the z in the numerator is 1. If it wasn't true, then when we did this process, right, if there was a coefficient on the x, we would still have to deal with it, right? Like if you just mentally, like if you just imagine that this was like 3x there, right? Then this would be 3x, and I would still have to divide by 3 at the end. So in some cases, you can just look at it, eyeball it, and get the answer. So I'm going to do that for L2. So the direction vector is 3/2, 6, and -9. And we got these two direction vectors, and if you want to know what if you want to proceed, this is how we do it. We need to check if they're the same direction vector first before we do anything else. So how do we do that? I kind of shortcutted it previously by just realizing that you multiply by 3, you multiply by 3, but then you don't multiply by 3, so they're not scalar multiples of each other. Here, you could do the same thing, right? If you wanted, like to go from here to here, you multiply by, what do you multiply by? -3/2, it looks like, right? But there's a formal way to do that where you just divide these out. you just do like -1 over 3/2. Like you divide out the x components, and then you divide out the y components, and then you divide out the z components. That's not right. And you divide out the z components, and you see what you get. And in this case, you get -2/3. In this case, you get -2/3. And in this case, you get, there shouldn't have been a minus there. In this case, you get a -2/3. And since they all divided out the same, what that means is the direction vector, yeah, they're scalar multiples of each other. Basically, if you took d2 and you multiplied d2 by -2/3, you would get d1. That's what we just determined. So the direction vectors are scalar multiples of each other, which means they go in the same direction. That means, according here, they're either the same line, or they're parallel, depending on whether or not, they actually overlap each other. So do they overlap? Are they the exact same line? Well, just try to figure it out by, there should be, if there's a point on one of them, the same point should be on the other one. So how would you check that? Well, you kind of got to just plug in a point that's on one of them. So like, just trying to look at my equations here. Okay. So let's see. Are they the same line though? I don't know. So visually, I can identify that on L1, if you put a 4, so if you put a 4 in for x, you're going to get 4 minus 4, which is 0, right? So the first fraction becomes 0. And if you put a -5 in for y, then the second fraction will be 0. And if you put in a 1 for z, the third fraction will be 0. So this is just an easy way to get a point on L1. So this is a point on L1. Is it on L2? Well, you would have to figure that out by seeing if, when you plug that point into L2, if those equations are satisfied. So try to plug it in. So L2 with this point plugged in, so it would be 4 minus 2 over 3/2. It would have to equal, but I don't know if it is, y plus 1 over 6, which is -5 plus 1 over 6, which would have to equal z over -9, which is 1 over -9. And then just working this out, this is -2 over 3/2. This is -4 over 6. And this is -1 over 9. And so I see, just like that's -2/3, that's not -2/3, right? So different. So 4, 5, 1, that point that I came up with on L1 is not on L2. What's that mean? Well, it means this. So the directions are the same, right? So you've got L1, and we have this point on it, which I'll just write P. And we know L2 is also in the same direction, but it doesn't have P. So if it had P, just if you just think about this a little bit, if it had P, it'd be right there on top of L1, but it doesn't, so it's like this. So it's not in the same place. So what does that mean? It means they're going to be parallel. All right, so that's a lot of work, but you know, some of these are a lot of work. All right, so number 4, I know number 4 was a little tricky to some of you, but the actual idea is pretty simple. So it gives you 2 points. So it gives you this point, I'm going to call it P, doesn't matter, 1, 0, 2, and I'm not going to bother drawing it in the right place. And then you've got another point, I'm going to call it Q, and it's 3, 4, 0. And people are like, oh, there's 2 points. How am I going to find the equation of a plane? I don't get the problem. Okay, but what's going on here is this. It doesn't say to find a plane between 3 points. It says find a plane containing all points that are equidistant from these 2 points. So what it's saying is if you go from P to Q, and I don't know why that just erased. I don't know why I erased again. And you go halfway, there's like a plane like that that's exactly halfway between those points, right? Like it goes through, right? There's like a plane exactly halfway between those points. And it's equidistant from both because like if you take a point here, for example, and you said like, what's that distance? Then it would be the same as that distance. Okay, so that's what's going on. And if you understand that, then this is actually very simple because in order to get a plane, you just need a normal vector and you need a point. So a point on the plane, well, how about this point, right? Wouldn't that be the easiest point to find? That's just the midpoint between the 2 given points. So the midpoint between P and Q is this point, and that point's on the plane. So a point on the plane is the midpoint of the line segment connecting P to Q. I'm just going to say PQ vector as a shortcut, but the midpoint of the line segment is really what I should say. How do you find it? What are we going to call it too, by the way? How about R? So all you're going to do is you're just going to add up the values and divide by 2, right? It's the average point. So like the x values are 1 and 3, so like 1 plus 3 over 2, right? I just took that and that, divide by 2. So the y value will be 0 plus 4 over 2, and the z value will be 2 plus 0 over 2. So it's literally just the average of those 2 points. So 4 over 2 is 2, 4 over 2 is 2, and 2 over 2 is 1. So this is the point on the plane. That's half of what you need. The other thing you need is a direction vector, a normal to the plane. A normal to the plane, well, how about just PQ, right? The line segment between these 2 points is normal to the plane, right? That's how it was defined. So a normal to the plane is, how about just PQ? Now you could do PQ or PR, right? Or you could do PQ, QP, PR, RP, RQ, QR, right? There's 6 different vectors technically you could find here. It doesn't matter which one you use. So I will just use PQ because why not? So that's the vector 3 minus 1, 4 minus 0, 0 minus 2. So that's the vector 2, 4 minus 2, I think. It is. So that's your normal vector. And then now, once you have a point and a direction, then you can just go to the equation of the plane. So equation of the plane. So again, there's 2 ways to do this. I'll write ax plus by plus cz equals d. Your direction is 2, 4, negative 2. I need to calculate the d by putting in a point. The point that's on the plane is r. So put in r, which is right up there at the top of the screen, 2, 2, 1. So 2, 2, 4, 2, 2, 1 equals D. So we have 4 plus 8 minus 2 equals D. So that's 12 minus 2, which is 10. And then my final equation will be 2x plus 4y minus 2z. Now we know D. D is 10. And just like before, you can divide all those by 2 just because everything happened to come up even. But I'm not. Okay, so that is how you would do that. Next question here. 5. All right, so these are basic operations. Also, I used the IJ notation here, but you don't need to. So like A is 4 to negative 1. B is negative 2i plus 2j, and then there is no k, so that makes it 0. Okay, so so we have these two vectors here, and we just need some operations. So of course, magnitude A is just square root 4 squared, 2 squared, 1 squared, which is root 21. 2a plus 3b, you just work that out. So 2, 4, 2, negative 1, plus 3, negative 2, 2, 0. So 8, 4 minus 2, plus minus 6, 6, 0. Then 8 minus 6 is 2. 4 plus 6 is 10. Negative 2 plus 0 is negative 2. There's your answer. That was B. And so on. You know, C is a dot product. A dot B. So 4 times negative 2 plus 2 times 2 plus negative 1 times 0. So it's negative 8 plus 4 plus 0. So it's negative 4. And then finally a cross product, which I guess technically in this video I haven't done a cross product yet. Because, you know, that was in the previous video that I erased. But I, J, K. And then you put in your vectors. So A, yes, where's A? 4, 2 minus 1. And then your B is negative 2, 2, 0. Isn't it negative 2? Negative 2, 2, 0. And there we go. So the way you do this is, of course, I, and then if you cross out the row and column for I, then you are left with these 4, which is 2, negative 1, 2, 0, and then minus j, and they do the same thing for j, which, you know, going to be too lazy to do that, but cross those out, and you'll have the 4 left over are 4, negative 1, negative 2, 0, and then you do that for k, and you have 4, 2, negative 2, 2. 4, 2, negative 2, 2, I think. Yeah. So then you have to do a 2 by 2 determinant on those sections. So 2 times 0 is 0 minus, negative 1 times 2 is negative 2. And then we have minus j. Don't forget the minus. Same thing here. 4 times 0 is 0. Minus 1 times minus 2 is 2. And then plus k. 4 times 2 is 8. Minus 2 times negative 2 is negative 4. So we've got 2i. Then we've got plus 2j when you combine the minuses. And then we've got 8 minus minus 4, which is 12. So plus 12k. So when you do the cross product, it'll work out like this in IJK notation. And then you can put it in the triangular bracket notation if you want. Okay. Of course, these operations are easy to do, like on Wolfram Alpha or another site. How are we doing here? Oh, there's so many freaking questions on this. We need to speed this up. Okay, so what's going on here? Hopefully the questions get shorter. All right, 6. Plane perpendicular or parallel to this plane. Okay, so pretty much there's not really anything to it except what we said here. So the plane is 2x plus 5y minus 3z equals 10. So a parallel plane, any parallel plane to that plane, is still 2x plus 5y minus 3z, right? Because if it's parallel, it has the same direction. It means it has the same normal vector. So 2, 5, negative 3. But the number at the end is going to be different. So all you have to do is recalculate this d, and then you'll have the equation of the new plane. So this is really just, you given a normal vector and a point, can you find the equation of the plane, which we've done twice already. It's easy. Trying to zoom in, it's not letting me zoom in. So if you were wondering what's going on. Yeah. So parallel plane looks like this. We need to plug in 1, 0, 1 to find d. So you put in a 1, 0. Don't have a minus sign there. Confused me. So we have 2 minus 3 equals d. So negative 1 equals d, I hope. And then once you have the d, then the equation is going to be 2x plus 5y minus 3z equals minus 1. Right? Same normal vector, but the d moves it around. So this is our new plane. And that's all there is to it. 7. Vector in direction 2, 4, 2, but length 6. Okay, very straightforward here. Okay, so this vector is not a unit vector, right? But you can make it a unit vector. So a unit vector, right, the way you normally get it is you take whatever vector you're starting with, v, and divide it by its own magnitude, right? So a unit vector for us would be 2, 4, 2 divided by the magnitude of 2, 4, 2. So 2 squared plus 4 squared plus 2 squared. So it's 2, 4, 2 over square root of whatever. So what do we have? We have 4 and 4 is 8, 8 and 16, so it's root 24, I think, right? Yeah, so root 24. So this right here, the point is, right, the whole point of doing this is that this has length 1. That's what dividing by the magnitude does. It makes it a unit vector. So length 1. So to make it length 6, just multiply by 6. Why 6? Because we want the new length to be 6. So that's all you do. You just say, okay, so how about 6 over that root 24 and then 242. And I could have, simplified that somehow, but I'm too lazy. Right? So divide by the magnitude, that makes it length 1, and then multiply by whatever your new length is supposed to be. And very simple. All right. 8. Right, classify the surface. 4x squared plus y squared plus 4z squared minus 4y minus 24z, what was I thinking? Plus 36 equals 0. Now, I could tell you that in other semesters, I have done a lot more with graphing these things than we're doing. It's just hard to do on an online class. Um, but what I meant you to do is um, we would be able to tell what this is if we complete the square. So like if you take your x's together, right? Like your 4x squared, and then I guess that's the only x. But then your y's, you have a y squared and a 4y. And your z's, you have a 4z squared and you got a negative 24z. So if you kind of just group these, 4x squared here, and then your z's, which I'm going to be sneaky, your y's actually. Your y is y squared minus 4y. I'm going to leave some space. And then your z's, I'm going to factor a 4 out. So if I factor out a 4, I've got z squared minus 6z. I guess I want to leave space, but I can't. Plus 36 equals 0. Okay, well, that's not good enough. How do I make that go away? Go away. No, that's the exact opposite of going away. Go. Okay, we'll do that. Okay. Okay, so for completing the square, the x's are done. Leave 4x squared, 4x squared. In here, completing the square, what you do, if you don't remember, is you take the middle term, oops, like by middle term, I mean like of a quadratic. So the middle term is the one with degree 1. So you take the number there, whatever it is, divide it by 2, and you square it. And that's like a magic number. So negative 4 over 2 is negative 2, and then negative 2 squared is positive 4. So what I want to do is I want to add 4 here. But if you add a 4 there, you need to add a 4 to the other side of the equation, right? Because we can't just add a 4 because we want a 4. Same thing here. You take the negative 6, divide it by 2, which is negative 3, and you square it, and it'll be 9. I put plus 9, but it'll be equal to 9. And that tells you that you should put a plus 9 here. But you need to add that to the other side as well. And you have to be careful because it's a 9, but really it's a 4 times 9 because it's in the parentheses. So 9 times 4 is 36. So I'll do like a plus 36 there as well. So then what we're going to do is look at what we've got. So 4x squared is 4x squared. Your y terms are going to factor. How are they going to factor? Well, the way we picked this 4 was magically so that this is a perfect square trinomial. So y squared minus 4y plus 4, if you factor it, is y minus 2 squared. And by the way, the minus 2 is what minus 4 over 2 was. Minus 4 over 2 is minus 2. That's that minus 2. So this is this. Sorry. All right, next one. We got the plus 4. And then in here, this factors. What will it factor into? It'll factor into z minus 3 squared. Why minus 3? Because minus 6 over 2 is minus 3. So 4 and then z minus 3 squared. And then you have plus 36 equals, and looking at the other side of the equation, we've got plus 4 plus 36, which is plus 40. So at that point, you can just divide, or not divide, subtract 36 over to the other side, and this is your equation. So so that's your equation. And from here, what you would be able to do, hopefully, is recognize that like in basically like an ax squared plus by squared plus cz squared equals some positive number, I'll say like r squared, is an ellipsoid. When they're all squared like that, when they're all squared and all positive, it'll be an ellipsoid. And you can graph that, by the way, pretty easily. In Wolfram, you can, but like Wolfram, it's kind of a hit or miss whether or not it'll actually plot it. If you really want to plot it, I would recommend you go to GeoGebra. That's where to go to actually plot it. Start calculator, 3D calculator, and then I think we can just type it in. I'm just going to try like if you do x squared plus y squared plus z squared equals, like, let's say 4, right? So like that's a circle. We don't have that. If you start changing the numbers out front, right, it's not x squared, it's 4x squared, right? Which squishes it that way. And it's not y, it's y minus 2. So if you change that to parentheses, y minus 2 parentheses, it won't let me do parentheses. Okay, I just ruined it. Okay, sure. 4x squared plus parentheses y minus 2 squared, and then plus 4 parentheses z minus 3 parentheses squared equals 4. Did we do it or no? Because of the stupid parentheses. Oh, and it just erased everything I just wrote. That's just fantastic. I love iPads, don't you? Okay, I'm gonna try it again. I don't know what it is that makes it not. Okay, we're getting there. All right, so only the y is wrong now. It just decides it wants extra sets of parentheses and then erases everything. Okay, well, I give up because it's really frustrating here. If I had a keyboard where I could type, life would be good. See, it just magically decides if I try to type right here, it puts the parentheses at the end. So it just won't let you do it. All right, well, I give up. Okay, well, I'm not going to keep trying to type that in forever. But the point is if you type it in, it's some kind of egg shape, which is an ellipsoid. Type it in on a computer, not a laptop, and you'll be fine. Don't do what I do. All right, so that's an ellipsoid. And you can see the center, by the way, by the minuses, basically. So like there's no x minus anything here, so the center is at 0. And then here it's -2, so that's 2. And then here it's z minus 3, so the center is 3. So that's the center. Not that you have to come up with that, it is. Okay. All right. 9, you have nothing, you will have nothing like 9 on your actual exam. This just kind of slipped in. Was this even on the practice test? I thought I erased it. Huh. I need to go back here. Life is hard. Oh yeah, it was okay. I was just making sure that I actually had the same problems. Okay. So anyway, back to this. So where are we? 9. So you don't actually have to do this, but just it says when they say orthogonal, right? You should read that as the dot product is 0. So like if A is orthogonal to B and C, that means A dot B is 0, and it's orthogonal to B and C, so A dot C is 0. So like both of those dot products are 0. Okay. And then it says A is also orthogonal to this vector. Then A is orthogonal to PB plus QC. So P and Q are scalars, right? So the idea is how would you check if A is orthogonal to PB plus QC? Well, you would do the dot product. So you would just check the dot product. What dot product? A dot PB plus QC. That's the dot product. And remember, P and Q are just numbers. So we check that dot product. How would you check that dot product? You use properties of dot products. So A dot PB plus A dot QC, that's distributive rule. Then if you have a constant, remember P is just a constant, that constant can come out. You can write this as P times A dot B plus, same thing here, Q A dot C. And then we already know those two dot products, right? Because they told us that A was orthogonal to B and A was orthogonal to C. So I know that when you do A dot B, you're going to get a 0. And I know when you do A dot C, you're going to get 0. So this is 0 plus 0, which is 0. And if you do the dot product between two vectors and you get 0, then those are orthogonal. So I can say, so A is orthogonal to whatever that was. PB PB plus QC, I think it was. The end. So, I mean, that looks hard, or when you first look at it, but it is very easy. Just orthogonal means dot product is 0. So, easy. All right. 10 and 11 are classifying, and 12 are all classifying surfaces. So these are all just going to be like looking them up. So, um, so y equals 3x squared plus z squared. I'm not going to do this, but like, I'm not going to go into great detail, but like if you were to plot this, and if you put the y-axis here and the, no, why would you do that? If you put the y-axis here and the x-axis here, and set z equal to 0, if you set z equals 0, then you're going to get y equals 3x squared, which is a parabola. And if you set, that should be squared. If you set x equals 0, you would have y equals z squared. And so if you look at that on the x z plane, then you also get a parabola, different one. And so what that's telling you is that your 3D shape here makes parabolas this way, and also it's hard to draw, but you know, kind of this way as well. I can't draw that, but the point is that you it's going to be one of these guys, right? Oh, except it was the y-axis, not the z-axis here. So my bad. This is the y-axis, and this should, what is happening to me? I put the z up there. That's what got me. If you actually graph this, then y equals z squared. This would be the z-axis, and this would be the y-axis. So x, y, z. So like the parabolas I was talking about were actually like these parabolas. So yeah, that's what happens, and it's like that. Okay, so that's a paraboloid oriented along the y-axis, or elliptic paraboloid. Don't feel like you have to memorize those. Remember that you can look them all up. If you need to, or even just plot them, right? Like there's nothing stopping you from coming here. I mean, other than, you know, wanting a calculator that works, delete, right? But like I can just type in, I think I can type in, if not, I know how to do it. Oh, actually, yeah, this is probably not going to work right, I think. But if it does, then good. If not, then we can fix it. Okay, it's fine. Yeah, so there you go. So that's a paraboloid on the y-axis. And by the way, like when I say like along the y-axis, and like you say like, well, how do you figure out along the y-axis? The axis that it's along is always the variable that's different than the others. So like if I put everything on one side, it'd be 3x squared plus z squared minus y, right? And if you're thinking about them, just look at the, this is squared. Oops, that's not what I wanted. This is squared, this is squared, and out front, this is positive and this is positive. And so this one has a different degree, it's 1, and also a different sign, it's negative. So y is the variable that's different than the other variables. And then that would tell you that whatever it is, it's going to be oriented along the y-axis. Okay, back here, next one. Where are we? We are on like 12 or something. Um, Is it 12? 11. Okay. So y squared equals 3x squared plus z squared. Again, if you put everything on one side, this is 0 equals 3x squared plus z squared minus y squared. So even though they're all squared now, this is still a negative out front, whereas this is positive and this is also positive, even though the degrees are the same. So whatever it is, it's oriented along the y-axis. Also, I can note here a few things. The things that you want to take note of are two of them are positive. So, well, first of all, they're all second degree, all second power. The other thing to notice is that two of them are positive, one negative. And then the third thing to notice is that there's a constant. In this case, the constant is 0, right? When you put everything on one side of the equation and leave the constant on the other side, the constant is 0. Constant is 0. So I know, first of all, it's along the y-axis. Whatever it is, it's along the y-axis because y is the variable that's different than the others. Now, what's the shape? Well, if you go to here and we go look at quadric surfaces, what you'll see, if I can find a list of them, just scrolling to look for a list, is that they all have different patterns of pluses and minuses. So look at this one. Ellipsoid, all second power, all positive, constant 1, or constant non-zero. That's not this, right? Because we have 2 positive, 1 negative. Okay. Now look at this one. Paraboloid of one sheet. X squared, y squared, z squared, so all second powers. 2 positive, 1 negative. It's plus x squared plus y squared minus z squared. That matches, right? 2 positive, 1 negative. But this one has a constant of 1, which is non-zero, and we have a constant of 0. So this is not a hyperboloid of one sheet. Looking down at hyperboloid of 2 sheets, you see all second powers, but now notice the signs. Negative x squared, negative y squared. Oops, that's 2 negatives and a positive. That's not what we have, so this is not a hyperboloid of 2 sheets. Elliptic cone. X squared, y squared, minus z squared, so they're all second power, 2 positive, 1 negative, and a 0 on the other side, right? So this is what we have. This is what we have. So an elliptic cone, or just generally called a cone. So this is a cone, and it's still along the y-axis because y is the variable that's different than the others. In the one that they listed here, right, z is the weird variable, the one that's different than the other two. So their cone was along the z-axis, which they must have a picture of. Here it is. Ours is along the y-axis. So if you were to plot ours, which you don't need to do, but if you did, if that's y, then we're looking at, I don't know why this is so hard for me to draw. Okay. Right, so it's along the y-axis. Ours is along the y-axis. And of course, you can just graph it in GeoGebra and see what it is immediately. But do you see how we look at the degrees, the signs, and what the constant is? And you would be able to do this by hand without, too much trouble. All right, so cone along the y-axis. Same thing here, number 12. So the trick is get everything on one side of the equation to look at the signs. So like this one, let's kind of cut that off. If you put everything on one side, it would be plus x squared plus y squared plus z squared equals 4. And at that point, ellipsoid is obvious. This one, if I put everything on one side, would be z squared plus x squared minus y squared equals minus 4. I don't like having a negative there, so I'm going to multiply everything by a minus 1, have negative z squared, negative x squared, positive y squared, positive 4. And if you go look at what that would have to be, if you look at what that would have to be, again, you should notice all second powers, 2 negative, 1 positive, right? And non-zero constant over there. It's a 4, but it could be like a 1 or something, and that's also the same. So constant non-zero. All right, so what is that? That is a hyperboloid of 2 sheets because 2 of them are negative, 1 of them's positive. So hyperboloid of 2 sheets. And where is it? This is also along the y-axis. And again, how do I know that? Because the z and the x are the same, and the y is different than the other two, in this case, because of the sign. So it's along the y-axis. So it's like this, but, again, tilted sideways. So it's not on the z, it's on the y. So that's what we're doing here. Okay. So I don't know how much detail we want to keep doing on these when you can just look them up at your leisure. Leisure is a fancy way of saying leisure. All right. But you can do these if you so want. Like on this one, if I move the 4 over to the left on C, and I move the z squared over on the right, it'll be a plus z squared minus x squared plus y squared. And what you can see, again, they're all second degree, second powers, 2 positive, 1 negative, non-zero constant, and that will tell you it's a hyperboloid of 1 sheet, right? 2 positive, 1 negative versus 2 negative, 1 positive, right? That's the difference between the previous one. Also, this is oriented along the x-axis, and I know it's along the x-axis because x is the variable that's different than the other two, right? It's the only one with a minus sign. So what's that tell me? Hyperboloid of 1 sheet. And there you go. D, when one of the variables is missing like this, it's going to be a cylinder because the variable that's missing could take on any value. So like y squared plus z squared is 9. That is, if you plotted that, right, like if you put y and z, y squared plus z squared is 9 is a circle with radius 3, is what that is. But then what about x? X can be anything. And so when you plot it, y, z, you have these circles, which are radius 3, but you can extend that circle along the x-axis and also backwards along the x-axis. It needs to be bigger. And you could, it didn't draw very well, but so you have a cylinder along the x-axis because the x variable is missing there. Okay, so that's recognizing surfaces. Couple problems where you're just kind of looking stuff up here. So the point here is this is a three-dimensional shape here, right? Where you've got, it's not like a cube, it's like a tilted cube, which they call a parallelepiped. Parallelepiped. And I say compute the volume using the triple product. And if you read the section, it'll tell you that this is a use of this thing. So the triple product is, so we got, I don't have the vectors drawn here. So if you label me a color, so if you label these with vectors, so V, doesn't matter which one's which, U, W, if you label the corners of like going from one corner as UVW, then the triple product or the absolute value of the triple product will tell you the volume of that thing. And there's some, complicated geometry why. But the triple product is, you can do U dot V cross W, or you could do any variation. So V dot U cross W, or you could do W dot V cross U, etc. The only thing is, after you calculate it, it could be negative, and if it's negative, you need to absolute value it in order to get the volume. And so that's just a basic formula, like that's how you can do it. So I'm not going to do that, but V cross W. So actually, you know what, I will, but I'm going to do it on a computer. So this is another thing that GeoGebra is good at. I mean, relatively. How come I couldn't? Okay, I'll just go here. If you put in these vectors, delete. So if you put in these vectors here, you probably have to. What? If I can't get a no keyboard, just no keyboard. Okay, well. So if you type in a vector, so you'd have to, like, for me, I'd have to go vector point. And I think I don't know if it'll work if I just go 200 here, or if I need extra parentheses. So this will be a surprise. Yeah. So I was supposed to give it a point, which means that the like that. Okay. So there's our first vector. The names might change because I'm not typing in the names. 20. And then last vector, we'll duplicate this again. 111. Okay, and so we got the U, the V, and the W in there, and then we need one of these. So you can do like this. So like, for example, if I want to calculate that first one, I can just say CROSS, and knows I want the cross product. I'll click on it, and cross product between a vector and a vector. I'm doing V and W, so V comma W. All right, and it called that A. So if I want U dot that, I would say U dot A. So I go dot vector vector. My first vector, if I'm doing this, is U, and my second vector is V cross W, but based on my previous input, I can see that GeoGebra called it A. And so I get -4. So right? So I do that, and that is -4. And that tells me that that triple product, which is just what they call the dot product and cross product of these three vectors like this, is -4, which means that the volume is +4. Okay, so easy enough. Is this the last problem finally? Oh no. Number 14. What's 14? Area of the parallelogram determined by U and V. Oh yeah, so this is just the other similar formula. So if you've got U and V like this, um, for any U and V, then you can kind of make this parallelogram. I didn't draw that long enough, but that should be U, V, and that should be U. And if you want this volume, then it turns out just to be the magnitude of U cross V. So, yeah. Or sorry, did I say volume? Area is magnitude of U cross V. So, well-known use of this. So you go to the 3D calculator. Again, this is all typed in. So I can do, maybe I can type in, I can get down here. So I can do the cross product. I can't if it won't show me the keyboard. Really, really frustrating here, laptop. Why would you? Okay. What's going on? CROSS. Cross product, vector, vector, U, comma, V. Okay. And there it is. And then I need the magnitude of that. Now I can see that the magnitude of that is 4 just by looking, but I can probably go magnitude, maybe. No, I can't. Um, I don't see how to do it on the screen keyboard, so I'm not gonna. But anyway, I can see that the magnitude of that is 4 because it's 0, 0, 4 basically. Okay, so let's get this back. So this is the magnitude of 0, 0 minus 4, which is 4. So that's also 4. And then last problem, and the last problem is just kind of a little bit of a thinking problem here. So the idea is this: we got a cube, supposed to be a perfect cube. It's not because I didn't draw it that well, but we have this cube, and we want to find a certain angle, and so it specifically says the angle between the diagonal of a face of a cube. So, like maybe the front face. That's the diagonal on the front face. Then it says of the cube with the diagonal of the cube. So the diagonal of a face would be corner to corner on one of the squares. The diagonal of the cube would be like corner to the opposite corner. So I didn't really draw it at a good angle for that, but from there to like there, for example, would be what we're looking for, or this picture is better. Now, in order to do this, what you need is a coordinate system. So like literally you just label all the corners. So like just think about putting your cube on, a set of axes here, right? X, Y, Z. So like, for example, this corner could be 0, 0, 0, right? And then up here, you would have 0, 0, 1. But then over here, you would have 0, 1, 1. Down here would be 0, 1, 0, right? So you have the 4 corners. But then the x value could also be 1. So you would have, this would be x value of 1, y value of 0, z value of 0. Over here, that's 1, 1, 0. This. And finally, the 2 up here are 1, 0, 1, and this one is 1, 1, 1. And so if you put in the sides that you're looking for here to here, for example, and I give that a name, let's call it U. U is, I can barely read my own writing, but it's from this one to this one. So if you find that vector, it is the vector subtraction. 1 minus 1 is 0, and then 1, 1. And then if I do another one for the diagonal, this one from here to the back one, that would be, I'll call it V, and you'd have to do, it'd be 0, 1, 1 minus 1, 1, 0. So it'd be 0 minus 1, which is minus 1, 1 minus 0, which is 1, 1 minus 0, which is 1. So you find those two vectors like literally as coordinates, and then now you can use the formula for the angle between vectors, right? So we know that the cosine of theta is normally, well, in this case, it'll be u dot v over magnitude u, magnitude v. So you just work that out. So like 0, 1, 1 dot negative 1, 1, 1 over magnitude of u, which is 0 squared, 1 squared, 1 squared, magnitude v, which is 1 squared, 1 squared, 1 squared. So what you get is on the top, when you do that dot product, 0 times negative 1 is 0, 1 times 1 is 1. So 0 plus 1 plus 1. And then on the bottom, you've got square root 2 and square root 1. No, square root 3. So you end up with 2 over square root 6. So then cosine theta is 2 over square root 6, and cosine inverse theta is cosine inverse 2 over root 6. And I don't think too hard about that. I just punch that into a calculator. Make sure your calculator is in degree mode if you want the answer in degrees. So like I can just go to, like, that would be good. Wolfram. So arc cos 2 over square root 6. And it'll give it to me in radians, but also degrees. So if I want it in degrees, 35 degrees approximately. So it's a weird angle, which, you know, based on the geometry, of course, it's going to be a weird angle. But that's the key to doing it, is labeling all the corners with values. Then you find the two sides that you're looking for are vectors, or the two vectors that you're looking for are corners to corners. And from there, it's just the angle between two vectors. Are we done? I hope we're done. Yeah, we're done. Okay, so that's it. I hope that was sort of helpful. Your real test is much easier than this, I think. I mean, there's still some stuff, but yeah, so that's it. I hope this helps somebody. And yeah, that's it for now.